Good evening, mathematicians and lay math enthusiasts. My name is Jeff Cook, and I am going to do a presentation here on a direct proof of the Riemann hypothesis, namely addressing some objections and counter arguments. And I think this is normal part of the peer review. So, if you are unfamiliar with our proof, I got a little distortion going on here. I do apologize. I'm going to move this back a little bit. Yeah, so if you are unfamiliar with the proof, you can go to just kind of type in your favorite search engine, go to Jeff Cook Riemann Hypothesis, or you can go directly to ResearchGate. And let me stop this share. I'll show you where to get that paper really quick. So I'm doing a Zoom. It's really a sloppy video we're going to do today, but it's okay because all I want to do is go through the counter arguments and address them. But here's where you get the paper. You go to ResearchGate, you'll see there's the paper with my co-authors, Dennis Pialin and Greg D. Volk. So this video, and we're going to go through it piece by piece. We have gone through it before, but there are some objections raised in the comments of the last video, which we just did an update just around January. When was it? It was like 2 weeks ago. And a really good set of counter arguments was put up in the comments, and I like that as opposed to just the ridiculous comments. I like all comments, don't get me wrong, I do read them. And I did say in the last video, which is this video, a direct proof of the Riemann Hypothesis 2026 and other proofs, I did say that I'm not going to comment in the or add anything to the comments anymore, but I did add one here, just let them know we're going to do this video. Alright, so we have to address all of these. Now, most of these videos that I do are just, I'm kind of talking, but since he put so many in there, it says 15, but there's 16 because I think he numbered 6 twice. No big deal. But it's going to have to go really quick. And in order to do that, I can't be doing my normal chit-chat and jibber-jabbering. So he wrote his down, so I'm going to write mine down. So let's go right to his first point. And let's go to the paper, and I'm sharing it now, and let's go. It's namely the first criticism is to the lemma, all right, which is right here. Okay, so please understand that none of these objections are accurate. They're very good objections, but they're things that we've already gone over, and so we know how to respond, and the paper was set up in this way to avoid any of these conflicts. The individual who posted this is anonymous, doesn't have any content on YouTube, but definitely seems fairly well informed mathematically speaking. So, but they're objections that only mathematicians would even know to raise. So I like that. But let's go over them. Let's see here. On another screen, I'm going to minimize the thing. All right. So, objection 1. Oh, and I should also say that they are all misunderstandings of what we're doing. So sometimes you got to read the lines and not just the equations and say, okay, what are they doing here with the equation? And a single statement can throw one way off course. And that is what happens in a large number of these cases, because I'm pretty sure this mathematician, when looking over these comments, will recognize where their objection falls short. And I don't mean that as a bad thing. It's just that, you understand, it took 17 years to come up with this proof, and we worked on it for years and refined it even for more years than that. So we kind of do know this proof like the back of our hands. All right, so let's go. Objection 1 is this, and you could read it in the comments there. So it involves the oscillator. The Riemann oscillator at t equals 0 is an identity by construction in one point. It does not offer any constraints on the zeros. And so there you see the lemma. And my response is, right. So what does that have to do with anything? Are we criticizing the lemma for not doing the job of the theorem? Are we trying to constrain the zeros with the lemma, or are we setting a foundation of this form of the zeta function? Well, that's what we're doing. We're not trying to constrain the zeros in this step. So the objection looks like it means something really but it doesn't. So I went over it, and it doesn't mean anything. So I'm going to address it and say, so you're right. Yeah, that's great. We aren't trying to constrain the zeros with a lemma. Anyway, so objection 2. This one is a little bit more important, actually, because this is obviously something that we've gone over quite a lot. The objection 2 is a function upsilon of s involving s and its complex conjugate s is not holomorphic in s. Analytic continuation does not apply in this case because the Riemann oscillator coincided in a point, not in its neighborhood. Therefore, as you have stated, this is his objection, upsilon is not generally analytic, but is in certain points. This is not enough. Upsilon needs to be holomorphic in S. This makes equations 4 and the step from 8 to 9 unjustified. Well, let's go look at equation 4 and see if there's any validity of what he's doing. There is 4. I think he means 3 and 4 because we defined this function alpha of 2 variables, and then we're describing the summand function here as 4. And let's go look at equations 8 and 9 so we can properly address this. 8 is the basis of the upsilon, how it's defined, how it's going to be defined. And so if you take the decay rate of an oscillator, which is, if you're unfamiliar with all this, just go watch some of the other videos. This is specifically a response to somebody who already knows the paper. Let's go here, and so 8 is just pretty straightforward, pretty straightforward integral, and it's equal to something very common and well known in physics and electrical engineering. So let me explain what he's saying. So this objection assumes that the proof is doing something it does not do. And this is pretty much a common thread with all of these objections, almost all of them. It's confusing 3 different notations: holomorphicity in S, legitimacy of algebraic limit-based manipulations, and 3, what is actually being analytically continued. So he has a problem with saying that upsilon needs to be holomorphic and analytic continued. So upsilon is not claimed to be holomorphic globally. This is stated in the paper, as he even acknowledged. What the objection is saying is that because upsilon of S contains the complex conjugate of S, all following analytic manipulations are invalid, and analytic continuation cannot be used anywhere in the proof. The only place where analyticity matters, however, is the Dirichlet series, the Abel-Plana representation, and the alternating series defining zeta sub f sub n. And that's not the same thing as the zeta function necessarily. All right, and those objects are holomorphic in the required domains. They are. Equation 3 is a function alpha of 2 variables, and it's analytic, and there's nothing unjustifiable leading to 4, as it is simply the summand function of 3. Step 8 to 9 is a series re-expression, but it's hard to say even if you know what you want to say. So a series re-expression. Right? So with convergence justified for a real part of S greater than 1, no analytic continuation is used there at all. And holomorphicity of upsilon is irrelevant to the step. Okay? It's not an analytic step. Upsilon of S is a parameter, and it's not a function being continued. So just understand that. And it is pretty clear in the paper, but sometimes, looking at it, you might miss that, and I get that. So, but just so you understand, we never analytically continue upsilon of S. We define it algebraically via a convergent Dirichlet series with, for real part of S greater than 1. Then we evaluate it pointwise. Pointwise definitions, of course, do not require holomorphicity. It doesn't. Pointwise coincidence is all that is needed. And the claim zeta sub s of 0 equal to 0 is a pointwise identity in T, not a neighborhood identity. So please understand that. That is sufficient. It's good enough because we never differentiate with respect to S and never invoke Cauchy type arguments in the S plane for upsilon. I hope that helps. Now, objection 3. Some terms are branching. Let's go to equation 5 because he's talking about equation 5. He mentions this kind of objection takes a couple different parts. They're similarly discussed. All right, so if you look in there, with equation 5, he's talking about the minus 1 to the power of s, the minus 1 over n to the power of s, the 1 plus it to the power of s. He says these are multi-valued for real valued s. For Abel-Plana construction, choice of branch matters. These terms cannot be treated as regular algebraic terms like in equation 5, nor do they cancel unless you pick and specify a branch. So just so you understand what this objection is really saying is because complex powers are multi-valued, the manipulations in equation 5 are ill-defined unless a branch is explicitly fixed. Therefore, the cancellations and the Abel-Plana step are invalid. This sounds serious, but it really misidentifies what's going on. The key mistake to this objection is that it assumes we are treating these expressions as free-floating multi-valued functions, when in reality all appearances of complex powers in the proof are already fixed by the standard principal branch used in analytic number theory. Nothing exotic or ambiguous is being done, and here's how you can see it. So it has to do with the decisive points. So we're not talking about t, we're talking about n. So that last equality in 5. So he's talking about t. So let's just look at it. These are single valued. Okay, they're single valued. In the Dirichlet and Ada series, n to the power of minus s equals e to the power of minus s log n, with real n real. All right, so minus 1 to the power of n is an integer valued sign, not minus 1 to the power of s. So no branch ambiguity exists in these terms. Minus 1 to the power of s appears only inside the Abel-Plana derived identities, where minus 1 to the power of s, or minus 1 over n to the power of s appears. It comes from analytic continuation identities, not from arbitrary exponentiation. The branch is already fixed by the same branch that defines n to the power of minus s and 1 plus it to the power of s. This is exactly the same convention used in Teichmar's, I don't know how to say his name, Stoppel, standard Abel-Plana derivations. If this objection were valid, Abel-Plana itself would fail in standard zeta theory. It doesn't. All right, so 1 plus it is handled symmetrically, and this is the most important part. In Abel-Plana, you have in any of these Abel-Plana formulas, let me see where, if I see it on here, down in equation 8, you see that 1 minus it to the power of s and then minus 1 plus it to the power of s. Both terms are evaluated on the same branch. Their difference is branch stable. Any global branch shift affects both equally and cancels in the subtraction. This is why the Abel-Plana integral is well defined. No step relies on branch-sensitive cancellation. At no point do we argue these cancel because the branches happen to align. All right, so instead, branch choice is fixed once, principal branch. All subsequent identities respect that choice, and this is standard practice. So this is not a hidden ambiguity. It's standard branch fixing. So hope that makes sense. To the one who raised it, it should now. Objection 4, this is kind of related to, objection 2 and 3. And once addressed, a lot of the remaining critique kind of starts to collapse. So this is kind of important one to address, and it is important for me to address all of these for the readers to know what they have and what they're looking at here is very solid in any mathematician. So let's suppose you're just kind of come across, well, I don't know if I want to defend or debate this proof. You're going to have to address these first. They were raised, and understand once you remove these, there's nothing else, and all of these can easily be explained. All right, so let's talk about objection 4. I need to drink water. Hold on one second. I don't have Greg or Denny on today, so I gotta do all the talking. All right. So this objection asserts. Oh, I gotta read it. Going from 5 to 6. Let's go to equation. Yeah, we're there at 5 and 6. Going from equations 5 to 6, the use of Abel-Plana citation is misleading because Abel-Plana is not robustly used here. The complex conjugate of s depends on s. Defining it as some symbol q does not remove such independence. Justified by proving the identity is uniform / analytic in q. Well, this objection asserts that we treated complex conjugate of s as independent parameter. It isn't. Therefore, Abel-Plana cannot be applied, is what he's saying. or she, unless you prove uniform or analyticity in that parameter. That's what he's saying, or she. But this is complete misdiagnosis of what the Abel-Plana step is doing. It sounds convincing, as uniformity conditions do matter in some analytic continuation arguments. Replacing complex conjugate by a symbol Q could be illegitimate if one were trying to extend holomorphicity in both variables. We're not. The objection assumed that Abel-Plana is being applied to a two-variable holomorphic function in S and Q. It's not. That was that other function I was telling you. In the paper, Abel-Plana is applied to the functions of the form, this is really basic, some function of x equals x plus 1 all to the power minus s. That is all this is, with a fixed s, or x, whichever. So Abel-Plana requires conditions on the summation variable here, x. F of x. So we I don't have this written out for you, so but if you kind of think about it, f of x equal to x plus 1 to the power minus s. All right. It doesn't require analyticity in auxiliary parameters. This is standard usage. Replacing the complex conjugate of s with q is a bookkeeping step. That's it. And when we temporarily write q in place of complex conjugate of s, we are not claiming q is independent of s. We are isolating the summation structure to show convergence and legitimacy. And after the Abel-Plana step, we substitute in q for the complex conjugate of s. This is a perfectly legitimate pointwise substitution. No uniformity in q is required because no limit is taken in q, and no analytic continuation is performed in q. Uniformity is not needed for pointwise identities, right? It's not. Uniform convergence would matter if we were interchanging limits in q or claiming holomorphicity jointly in s and q. We do neither. All claims are pointwise in s. This is exactly how parameters are handled in classical analysis. Same pattern here, and I have a few examples of that has done the same thing. Parameter dependent Fourier integrals, Mellin transforms with fixed parameters, and stable Abel-Plana derivations. If the objection were valid, huge swaths of classical analysis would fail. So I hope this point is grasped. As, like I said, the rest of the objections kind of fail quickly because of this one misunderstanding. Again, this objection assumes a two-variable holomorphic argument that simply isn't being made. We good? Objection 5. This is one of my favorites. The miracle. That's what he calls it. He says equation 15 appears to be a miracle. The authors should justify term by term. Well, I do believe in miracles, but I also believe in mathematics, and this is not a miracle. Let's just go down to it. All right. It's this very beautiful cancellation. That's what it is. So what the objection is saying is that the cancellation isn't clear. So they suspect, we just pulled it out of our rear. And that's not mathematical, he's not refuting that mathematically. It's just a presentation and critique, I guess. So if someone reads over this quickly, it can look like magic. My recommendation is take this slowly. It's routine algebra. Objection 5 says equation 15 looks like a miracle and should be justified term by term. Fair. It's compressed for readability. Okay, Greg is always pushing to, we gotta have this paper shorter, reduce. And so we get a lot of that. But in this case, the constraints were chosen so that the complex conjugate of S-dependent piece cancels exactly with the standalone, which is a little bit complicated, but minus complex conjugate squared over S minus 1 to the power of 3 term. So as you can see that there on the outskirts over there. So they were chosen so that do this. And what remains is precisely the infinite series that, which equals the zeta function for real part of S greater than 1. It's not a miracle. It's beautiful algebra. There's a difference. Objection 6. So no, we do not need to show those steps. You can easily, if you were to do this by hand on paper, as you all should be doing, you would get the same result. Maybe a few more steps in between, but those are the main ones, just showing leaving there, demonstrating what is the clear part. So anyone could break that apart with a piece of paper. It's not hard. All right, there. Objection 6. There's 2 6, so let's do the first one here. This one's important because it's where the critique tries to invalidate everything all at once. But it does so by misstating what the proof actually requires. So this is very important to address. Again, there's nothing we need to rewrite in the paper. It is clear in the paper. Sometimes you just got to read things over a few times to know exactly what we're doing and what's actually stated. Okay, and all right. So here's the objection. The ableplana construct has conditions. It is not generally valid over excuse me, over the entire complex plane. Extension to the complex plane requires holomorphicity, yet upsilon of S is not holomorphic in S. This makes the entire proof invalid because all analytic steps in the actual proof section require this holomorphism. All right, so they're asserting a chain like this. I kind of wrote it down here. So one, you got ableplana requires holomorphicity. Boom. That means, and then upsilon of S is not holomorphic. Boom. Therefore, ableplana cannot be used. Boom. Therefore, the entire proof is invalid. Well, this chain breaks at step one, which is the ableplana requires holomorphicity. Everything after that collapses. It sounds serious, but the objection pattern assumes the hidden premise, and it's this. The objection assumes this premise. Every object appearing in a proof about zeta function must itself be holomorphic in S. That is not true. That premise is false. Our proof does not require upsilon of S, the complex conjugate of S, or the absolute value of S to be analytic. And importantly, no analytic continuation step is ever applied to them. If the reader does not understand this, he or she is not going to understand the paper. So let me be clear about this point. All right, why they're not analytic and why it's okay that they're not analytic. What not analytic means here is that you would say that S, maps to the complex conjugate is anti-holomorphic. All right, and S mapping to the complex conjugate of not complex conjugate, but absolute value of S is not complex differentiable anywhere. Therefore, any expression involving them is not holomorphic. This is standard, undisputed complex analysis. But non-holomorphic doesn't mean invalid or unusable. It only means one cannot apply Cauchy-Riemann and one cannot invoke complex analytic continuation on that object. I know it's a little deeper than what you're taught in analysis 101, but it's very, very important if you're going to be refuting a Riemann hypothesis proof. You have to understand that, okay? Because we're using it and we're allowed to use it. So what upsilon actually is, this is important. Upsilon is not a function being analytically continued. It's not a holomorphic function in S, not a candidate for contour deformation or Cauchy arguments. Right? Upsilon of S is, however, a pointwise defined coefficient constructed via a convergent Dirichlet series / integral. All right, there's no hidden assumptions in it. That's why we chose it, and it's evaluated at fixed values of S. You got that? So the important distinction. All right, don't forget this. There are two different analytic layers in this paper. There's layer like 1A, let's say, objects that require holomorphicity, and that would be, the infinite series that defines the zeta function, the infinite series of n to the power of minus s, and then they also have the eta function, the infinite series of minus 1 to the power of n times n to the power of minus s, and in the ableplana integral representation of the zeta function. Okay, so these are the objects that are analytically continued. They're required to be holomorphic except at poles. They're objects that are treated with standard complex analysis. All right, all those conditions are satisfied there. Layer B, there's a second layer now where there's objects that don't require holomorphicity. All right, that would be the complex conjugate of S. Anywhere you might see the absolute value of S, upsilon, and alpha of S. All right, those are algebraic geometric parameters evaluated pointwise, never differentiated with respect to S. They're never analytically continued. Okay, no holomorphicity is required for them. All right, the objection is illogical because it assumes if a non-holomorphic object appears anywhere, then analytic continuation is valid everywhere, and that's just false. All right, and I can give you counterexamples. Let me give one a counterexample. So, because I said this is important, it's something we've been over years ago, and it's important to address so that we know every single little corner of this, because it's obviously something that's easily to be misunderstood. What you have is this: if you have an offset function, some offset of the zeta function, that's what we're talking about. That's what alpha is, and upsilon as well. So you have some function of s, f of s, right, equals the zeta function plus, let's just say, the absolute value of s squared. So we have zeta function offset by absolute value of s squared. All right, f of s is not holomorphic. That function is not holomorphic. Neither is alpha, neither is upsilon. But zeta function still is. And analytic continuation of zeta is completely unaffected. All right, this is so. What you can think of it is, it's not a linear shift, but it's an example of like a non-holomorphic perturbation. All right, so you're shaking something, you're attaching something to the zeta function. All right, the zeta function doesn't change, but we're just kind of disturbing it a little bit. Perturbation of, I don't know, it's a hard word to say, perturbation of a holomorphic function. All right, so adding a non-holomorphic term does not alter the analytic continuation of zeta function. It doesn't. It just produces a new non-holomorphic function. The analytic properties of zeta remain intact. All right, that's it. All right, so it's done. It's always been that way mathematically, and we're allowed to do it. Objection 6. Let's move on. This is the second objection 6. This one sounds, pretty devastating. It's not. In the comments, a reader might come across and go, "Oh, yeah, it's done." It's not. Here's the objection. Calling equation 18 a new representation is misleading. It emerges because upsilon was defined to make it true. Also, the authors should highlight the pointwise coincident nature of equation 18 due to the t equals 0 restriction made earlier. Let's see. Let's go to equation 18. We've been staring at 15 for quite some time here. All right. Equation 18. And this is a pretty important result. All right. So the objection is claiming two things together. It's saying that equation 18 is tautological or reverse engineered. It's us saying that equation 18 is only a pointwise identity and therefore weak or misleading. Neither claim is correct. But the second one is actually already acknowledged in the paper. And the first confuses normalization with circularity. Let's go over that. All right, in analytic number theory, people are trained to be suspicious of. This is why I understand this. And Greg is all over this. This is what it was always. Just we got to find any of these hidden areas of circularity. All right, and so in analytic number theory, people are trained to be suspicious of representations that look engineered, identities obtained by evaluating a single point, or constructions where parameters are chosen to force agreement. So the instinct behind the objection is completely understandable. I get it. The logic is wrong, and it needs to be carefully looked at. So the person who wrote this objection, do please look at this. Defining a parameter to normalize a representation is not circular. All right, so make no mistake about it. We did not assume the zeta function at all, and then define the upsilon of s. All right, so zeta function is already defined. And we didn't then rediscover the zeta function from upsilon. Okay, so that's what the objection is saying if you break it down. All right, what we did actually is define upsilon independently via Dirichlet-Abel-Plana construction. And we built an oscillator expression that depends on upsilon and the complex conjugate of s and algebraic terms. And then we proved that evaluating at t equals 0 yields the zeta function. That's all we're doing. We're starting with the integral definition, actually infinite series, and we just kind of taking the natural course of events of where it leads, and it leads to the zeta function. That's normalization, not circularity. And if you have a problem with that, then you have a problem anytime somebody defines the gamma function via an integral, and then chooses constants like gamma of 1 equals 1. Well, no one calls this misleading. And no one has a problem with it, nor would anyone have a problem with it if it had anything other than to do with the Riemann hypothesis. It's the same tool, though, and it's a tool that's available at our disposal, and we're proud to use them. It's used all the time in mathematics. So look over that one, check your math on that one. There's nothing wrong with it. All right, then there's the other point he had, or she, that equation 18 is pointwise. So, yeah, okay, so let's see exactly what their wording was. Hold on. Highlight the pointwise coincident nature of 18. Okay, here's the reality. This is the way it is. Equation 18 is pointwise, and that's it. It's sufficient. The objection says this is a flaw, but equation 18 is explicitly derived from the evaluation at t equals 0. No claim is made that holds it in a neighborhood in t. No analytic continuation in t is invoked. So yes, we get that neat little 18, which is the oscillator, or the new form of the Riemann zeta function. What I call it an oscillator form. All right, and so yes, that equation is a pointwise identity in t, and that's all that's required, because the oscillator is a formal analytic model. The proof of Riemann hypothesis does not rely on t analytic structure at all. All right, so the constraint on zeros comes later from alpha of s and r, which we're going to get to. It doesn't come from equation 18. A representation does not mean a new holomorphic function and a new analytic continuation with new analytic continuation properties. It just means it's the exact algebraic integral expression for the same object. That's all it is. If you want to spell it out for what it is, an exact algebraic integral expression for the same object. If one stutter, you'll be able to understand it better. But let's just wrap this up, because I want everyone to understand it. It's important for new readers to this paper to know that this is all handled very nicely in the paper. Equation 18 is new in the sense that it expresses the zeta function in terms of upsilon and the complex conjugate of s. And it does this without Euler products. Ooh, this is what really gets people frustrated. And it does it without Perron type formulas, because those are easy to object to. So now you're stuck with a completely new approach to the Riemann hypothesis, and you're trying to find a way where it has to be wrong. But if you take this and go step by step, there's nothing wrong with what we're doing. It's just your most reviewers and mathematicians in the area, they know where to look with what's been commonly done, and we did things differently. And we're no slouches, okay? Denny has his PhD in mathematics, and Greg graduated at Stanford, the top 1% of his class. I mean, I'm me, but we're no dummies, okay? So there's these things we have looked at. Let's move on. Objection 7. Okay. Equation 19. Let's go down to equation 19. Let's see. Where's my cursor? Okay. Equation 19. All right. In equation 19, the function z is not single valued for real t. He says the -1 to the power of t equals exponent of t log -1 is branching. So I kind of brought this up earlier in a different way. We're going to address it again in a different way too. And the trajectories depend on the branch. The description of a spiral geometric picture is misleading. No, it's not. All right, stop saying that. It's not. Our actual usage in the proof is about the alternating Dirichlet eta terms, okay? I.e. integer n. All right, so -1 to the power of n times n to the power minus s. All right, that expression is single valued and unambiguous. All right, please don't bring it up anymore. All right, while we mentioned this in the proof, okay, I suppose we could clarify it, further, but I mean, anyone seeing, we do state, okay, now we're going to switch, and these n are natural numbers, and they're in the, this stuff is, for anyone really understanding the zeta function, you don't even need to know the Riemann hypothesis, just understanding the zeta function, you're going to know this, And so it's single valued and unambiguous. Okay, objection 8. All right, let's go down a bit. Equations 28 and 29. All right. Between equations 28, this is the objection, between 28 and 29, the authors claim it converges pointwise to the analytic continuation of zeta of s for real part of s greater than 0 and s not equals 1. This is not true. The expression has additional poles beyond s equals 1, where 1 minus 2 to the power of 1 minus s equals 0, i.e. s equals 1 minus 2 pi k over log of 2. On these points, the expression is not analytic. So let's look what they're talking about. They're talking about the definition of the partial sum. Let's see, where is that on here? 28, yeah, so you see, they're talking about this. And the claim that it converges for a zeta function for real part of 0. Let me just sum this up. It's a typo, obviously. It's a typo. Come on, you see this. That's supposed to be real part of s not equal to 1. Of course. But that's a typo. I mean, good catch. He's saying it's like we're claiming all this stuff. It's just like, you know, it's a typo. Anyone? All right, so what are you saying? So this term out here, the 1 over 1 minus 2 to the power of 1 minus s. Okay, that is zeros when the real part of s equals 1. All right, it's not in the critical strip, but it's true that you can't say, you know, that it converges for real part for all of these a real part greater than 0. That's true. There are those points where the real part equals real part of there, but this is real part of s equals is not equal to 1. And that gets rid of all of those ones. And I changed it in the paper, but there's nothing more to say about that. Obviously, if you know that, he's right. But it in that sense, just change that s to s not equal to 1, real part of s not equal to 1. It doesn't change anything for the hypothesis. It's not even an issue. It's just a typo. Let's move on to point 9, and he knows it now. And I'm explaining it's just a typo. He probably knew it already, but it's a good way to break apart a proof. You know, you can't assume typos. You know, you can, hey, this is what they say, and it's wrong. And I get it, but you know, you kind of know the domain we're talking about. Like, look, like, you know, he should know what we meant. So, you know, if the eta function shares all the zeros of the zeta function of the domain we're interested in, the critical strip. But I concede, you know, the typo is ugly, and I fixed it. So. Not an issue. Objection 9. That's equation 25. Let's go back a little bit. Okay, alpha. Oh, I love the alpha function. This is my favorite. This is where everything works. The rest of these kind of are all going to be grouped together. Yeah, they're all kind of crumble in the same way. And that's good for us, but it's also good for the reader to understand how we address that, you know, these questions that are raised for them, because, like I said, they are good questions. They are, but they're good questions like on the surface. But anyone, like a reviewer should know these things, you know, and address them and say, how you got to change that, you got to do that. I put a little note here that you mean that. They should be understanding what's going on, unless they're just skimming through it so quickly, eager to just throw errors out everywhere when they're really not errors. But they're very important for me and our side because, well, one, I love to talk about the paper, but two, because it does help clarify for other people out there the meaning. All right, so let's, objection 9. From equation 25 to equation 26, let me just scroll down a little bit. Yeah, this one's really awkward objection. I think it misunderstands what we're saying. Well, I know it does. All right, but here, let me read it. The authors confuse a summand with a factor. Second, they assume a form alpha of s equals b b of s plus c of s times zeta of s, and reduce by setting zeta of s equals 0. And you can go read these comments. They're in the other video that you saw at the beginning. He has them all there listed. All right, and reduce. It has this form, and then reduce by setting zeta function equal to 0 to alpha of s equals b of s. I'm not sure what he means by that exactly, but from the construction as a pointwise coincidence, while alpha encodes zeros of zeta, they falsely follow that zeta of s equals 0 implies alpha of s equals 0, which is not true. You're right, it's not. It's not what we said. No proof of alpha s equals 0 if and only if zeta function equals 0 has been established. So again, this objection mixes up what we're assuming, what we're defining, and what we're proving. First, there is a loose, informal habit, especially in physics and some other math, of saying things like the factor that determines 0. All right, meaning the part of the expression that controls vanishing under constraint. So, yeah, it's not standard in math. Okay, I get it. And so I'm going to change the word to isolating the offset, and instead of a factor, it's the offset. Yeah, we're not multiplicatively deconstructing it. We're additively deconstructing it. All right, so I changed that. But let's go to the main point here. We don't assert that zeta function of s, zeta of s equals 0 implies alpha of s equals 0. We don't. We assert and prove that the offset k, which is this, we don't define it yet as k, but we later do. See that in 27, that over there on the minus side. Let's see if we get a better one. Let's go to alpha to 25. The first equality, you see where my cursor is? That term right there, that's the offset. All we're saying is we're taking that offset, expanding it out, and we're showing that that offset equal to 0 implies real part of s equals 1/2. And that is very, very straightforward algebra. Complex arithmetic, but it's still just algebra. Okay, we're not saying that all zeros imply. We are saying that that offset equals 0 if and only if the real part of s equals 1/2. And it's just a simple misunderstanding. But so it's a completely different statement than what we're saying. So if we're doing that, then I'd say, well, he's right, but we're not, and he's got to look over that and see, no, we're not doing that. Obviously, it's clear once you read it over again. Objection 10. In the definition given in equation 29. All right, let's go to 29. All right. Very beautiful, beautiful thing we're doing here. Drink water. And let's read what he says. In the definition given in equation 29, vanishing terms are described. It has not been shown how these terms vanish. No rate and direction in the complex plane for them vanishing has been derived, and the denominator zeros are excluded. This should be shown explicitly. I object. I object to this objection. Even if the denominator vanishes for finitely many indices, this does not affect the limit. Moreover, when k does not equal 0 and g of n goes to 0, the denominator is bounded away from 0 for all sufficiently large n, because limits ignore finitely many terms. This is why nobody has ever raised this before. It's just simply not right. We should not show that explicitly. We don't. I don't care if there's any, not that there are any, not that there could be any, but even if they were, it doesn't matter. Limits ignore finitely many terms. That's what they do. Now, what vanishes is standard and already implied. So, real part of s greater than 0, for real part of s greater than 0, the individual term of z function, which, let's go to that really quick. Yeah, 19. Okay, swap out t with n, which we say we're doing at 20. The natural n values of t. Okay, and we shouldn't define that. We shouldn't define that as t. We should just note it as being a spiral, and we're taking the pieces n of that and using it to 21. Okay, but I just wanted to mention that. All right, the individual term of z at any n satisfies the absolute value of z equal to n to the power of minus real part of s, and that goes to 0. It just does. All right, so absolute value, if you take the absolute value of z, reduce what it is. It's n to the power of minus real part of s. That's a smooth function, and it goes to 0. It's just the way it is. The eta partial sums satisfy that. Okay, so that's all that's meant by vanishing in the numerator denominator expressions of r, or r sub s of n. The parts involving z sub s of n or zeta of s sub n tend to 0 under the stated hypothesis. All right, so that's just, yeah, I don't know. One doesn't need a direction. Oh, he mentions direction too. So one doesn't need a direction in the complex plane because we're controlling magnitudes. We're taking absolute values. So direction demand is misplaced. The ratio is defined in moduli specifically to avoid directional phase issues. If this isn't clear, maybe sit down and go over again. It'll become clearer the lighter you hold the reins to this problem. Loosen your grip, just fall back on the basics, and don't overcomplicate what we're doing. All right. Objection 11. Again, I am very grateful for these objections. So don't. My response is personal. It sounds personal, but that's only because the objector is anonymous. So I can make him out to be whoever I want it to be because he chose to be anonymous. So I'm making him out to be like my worst enemy, even though I'm very grateful that he is raising these. But I'm going to kind of have that attitude a little bit because it feels better. Objection 11. The step from equation 30 to 31 is unjustified. No, it's not. Let's go to it. 30 to 31. Trust me, if you were a mathematician and we're not incognito, I would answer these with so much respect, so much more respect. But be that as it may. The step from equation 30 to 31 is unjustified. Okay. Equation 30 includes moduli, and solving for k introduces branching and is non-invertible. He loves that branching issue. The equation r equals the absolute of k minus a over absolute value of k minus b does not have unique solutions for k. It defines Apollonius circles. All right. I do know what these are. Don't know how to say it. All right. Apollonius circles with infinitely many solutions. Only two branches arise if k is restricted to be real, but k is complex. So, he says, the derivation is incomplete. Okay, let's break this down. The equation, if we're looking at k and r in here, what do we have? So he was mentioning k minus a over k minus b. So k minus a on the numerator over k minus b, right? So let's look at that for a minute. The absolute value of k minus a equal to r times the absolute value of k minus b. So we're just going to solve for absolute value of k minus a. That defines an Apollonius circle in a complex plane, hence infinitely many solutions. That statement is correct, but it doesn't apply to what we're doing. We're not saying, given R, find all possible K contained in the complex domain satisfying 30. All right, we're not saying that. The situation is this: K is already fixed. All right, it's equal to s minus 1 squared minus complex conjugate of s squared all over 2 over times s minus 1. Okay, A and B, if you want to treat this is A and this is B, are functions of n that tend to 0. Okay? In this proof, we're saying, okay, we're only going to talk about the zeros. We don't care about anything else. We're not dealing with anything other than the zeros at a certain point. This is what we're focusing on. That is going to tend to 0 because we're saying it's going to be a 0. This always goes to 0 because the absolute value is a smooth function that goes to 0. And that's pretty straightforward. But here we go. A and B are functions of n that tend to 0, right? R sub s of n is defined from that fixed k. Equation 30 is not an equation to solve in an abstract. Make sense? It is an identity constraint. That's it. Relating quantities that are already defined. So the Apollonius circle objection attacks a completely different problem than when we're solving. Equation 31 is not solving a modulus equation in general. What we do between 30 and 31 is just this. We assume R is a finite real limit. And then the next thing we do is we express the algebraic consequence of that limit. And the next thing we do is analyze which limits are compatible with the identity. We're not claiming uniqueness of K from the modulus relation alone. This is important because we are analyzing necessary conditions for consistency. We're not constructing all solutions. So we're saying, hey, if it's true, then it's going to lead to this. If it's not true, it's going to lead to that. So why only R equals 1/2 or R equals 1 appears? Well, this is not because of choosing branches. It's because if K does not equal 0, both the numerator and denominator tend to absolute value of K. All right? If this is 0, where is it? Where this term's 0 and this term's 0, then we have K over K. That's 1. But if we have something else where K is going to 0 as well, we may end up with another constant. And sure enough, that is without a doubt easy to prove that it is 1/2. There's only 2 possible choices. This is not because of choosing branches, but because it tends to K if it's K is not 0. So R going to 1, unless cancellation forces something else. Cancellation requires K equals 0, and K equals 0 implies reverse implies. So if and only if real part of S equals 1/2, and that's from that other proof. It's very down below. That's why we did it here in this order. See that right there? That proves K equals 0 if and only if real part of S equals 1/2. This is, again, that was that basic complex arithmetic. If there's such a thing. There is. But. Okay, so, yeah, so what we're saying is the values R1, or R equals 1 and R equals 1/2 are forced by the asymptotics, all right? Not by solving a modulus equation. In short, equation 30 is not solved for K as a free complex variable. K is fixed by S, and the equation is used to analyze the limiting behavior of R as n goes to infinity. The Apollonius circle criticism applies to completely different math. It's not even the same problem. And let's go on to objection 12. This is basically objection 11 continued, plus a limit for, denominator nitpick. That's basically what equation objection 12 is. All right, due to 11, equation 32. All right, let's go up more to 32 again. All right, due to equation 11, equation 32 is incomplete and does not cover all solutions. Also, equation 32 contains R sub S of n minus 1 in the denominator, while in equation 34, a limit R sub S of n equals 1 is used. That's dividing by 0 in equation 32, since there is no controlled cancellation. Okay, let's go up and look at, it's not true. We've got to discuss it though. 11, let's go to equation 11. So upsilon again. All right, due to 11, equation 32 is incomplete and does not cover all solutions. All right, so he's saying that we have a dividing is 0. All right, so it's the same underlying mistake as objection 11. Let's go back to 32. Let's see if I can clarify this in a way that's easily understand. All right, you're treating equation 32 as if we're trying to solve a general modulus equation and list all possible solutions. Our paper isn't doing that. We're not classifying all solutions in K or Z. We're working with a fixed K, a specific Z sub S of n, equal to minus 1 to the power of n times n to the power minus s, and a defined ratio. Okay? And then we're asking about asymptotic compatibility as n goes to infinity. So incomplete solution set is not a relevant criticism unless we claim to solve the general Apollonius circle problem. We didn't. We did not. We are not enumerating all algebraic solutions of an absolute value relation. We are analyzing the limiting behavior of the specific R defined by our K, Z, and zeta function, or the partial sum of the zeta function. We are allowed to manipulate equations involving R sub s of n minus 1 for finite n where R doesn't equal 1, and then take limits afterwards. Why this is not an error? Because, well, nothing forces one to use the equation when R goes to 1. We're not requiring you to do that. Limits don't license division by a term tending to 0. So you're saying that we're forcing you into this situation. I'll show you what we're not. All right. Limits don't license division by a term tending to 0 unless one handles it carefully, okay? And we do handle it by stepping back and treating R equals 1 separately. So we're going, you saw in the paper, it said, now return back and go do the other thing. So we're not, what we're doing is we're going through and seeing what is the consequence if we take these steps. And guess what? We're not saying R does equal 1. In fact, we're saying the opposite. We're saying it can't equal 1. That's what the whole point is. It's that it can't equal 1. We're not required to check 1. We're saying this is the consequence if we were to let R equal 1. Do you understand that? We state this explicitly in the paper. Please understand. All right. If we say, let's say we're going to divide this by 0. What is the natural consequence of what we're doing? Well, this step is bad. All right, the first step, we can't do that. If we say we're going to let s equals 1 or no, we're going to let it say 1 over s minus 1 equals something. We're allowed to do that. And then all of a sudden, at the very end, we say, okay, now go back and apply s equals 1 and see what happens. Boom, you'll see why it doesn't work. Okay? There's a number of things. All we're saying here is R doesn't go to 1. All right? It's not. We're showing what the natural consequence would be. All right? So even if there was something that divides by 0, we're saying that it's invalid anyway. And that's why further reinstates the proof. The limits must be 1/2. All right, I said that enough. Objection 13. Yeah, so just long story short, consider them 2 separate steps, and you're not forced to do either of them. Just look at the implications of what happens when R goes to 1. Work it out on your own paper. It still ends up giving you the same result we have. All right, objection 13. This one is a direct consequence of the same misunderstanding from 11 and 12, equations 1 and 12. So the last two. So if you misunderstood those last two, which are very similar, then you understand why 13 came about. But it's worth answering because it sounds, kind of, if I were to not answer, it sounds pretty nasty. But it's really straightforward. All right, equation 33. We're on 33, good. Equation 33, solving for z leads to an expression that, due to the modulus operations before, is not equal to the definition of z, which was minus 1 to the power of n times n to the minus s used earlier, forcing terms to be equals unjustified. All right, so they're saying because absolute values appear earlier in the definition of R, we cannot later solve for z as a complex quantity. And he's saying that the absolute values destroy phase information, I guess you could put it. Therefore, equation 33 can't equal z equal to 1 minus 1 to the power of n times n to the power of minus s. Yeah. If we were literally trying to invert an absolute value equation, this would be correct. But again, it's not what we're doing. The key misunderstanding, again, is we're not doing this. We're not doing given absolute value of k minus a over absolute value of k minus b equals r given for b in general. That would be invalid. What we're doing is starting from an identity that already holds for our specific objects. That's k, that's z, and zeta function. These objects, these conditions already hold. This identity already holds from those. Defining r from those objects, that's all we're doing. And then we ask which limiting behaviors of that identity are compatible as n goes to infinity. Okay, so equation 3 is not a solution extracted from moduli. It is a rearrangement under the assumption that the identity holds for the actual z sub s sub n, right? This is a necessary condition argument, not a reconstruction argument. That's the way to look at it. And I think that's all that needs to be said of that. Objection 14. This is actually one of the weakest of the remaining objections. Once everything else, we kind of clarified everything else. This one's very weak, but let's get into it. I got to answer them all. And it's fun to do. All right. He says, equation 34, we're still right here on 34. The limit for terms in equation 34 is not established. It is implied that all terms converge to finite, non-zero limits, but there is no proof. All right, so what they're objecting to is that in the equation 34, they're objecting to they're claiming that in passing to equation 34, we implicitly assume that various expressions have limits. Okay, they're saying those limits are finite, and none of those limits vanish or blow up without justification. They're saying we do this without justification, and it sounds serious. But in our case, the limits are, one, known, or irrelevant, because the argument is conditional if the limit exists. See? So it's either known or irrelevant. That's what we have to deal with. So the logic of this part of the paper is this. Assume limit of r sub s of n exists. Assume it exists. If it doesn't, we're not interested in it. It's not a zero. But assume it exists. Then analyze for which values that limit are compatible with the following identity. We're not claiming that the limit exists for all s. In fact, I think we even stated in there it doesn't. I don't remember. We used to anyway. But it doesn't matter. We're not claiming that. All right? And we're also not claiming that all component expressions converge individually. We're doing standard conditional asymptotic analysis. And that alone kind of neutralizes most of the objection. Mainly the zero limits, not being excluded. All right? So let me just wipe out the rest of the objection. Objection 14 says that limits in equation 34 are not established. But the argument, there's conditional. We assume the limit of r sub s sub n exists and ask which values are compatible. The only convergence used is standard n to the power of minus s goes to 0, which it does. It's very typical for a real part of s greater than 0. And the eta partial sums converge when zeta function of s equals 0 because they share the same zero as the critical strip. No claim is made that all limits exist unconditionally. Equation 34 simply enumerates the possibilities if the limit exists. And I think if you take that slowly, you'll understand where we're going with that, or what I mean by that. All right, objection 15, last one. I'll spend a little extra time on this one. It's our last one. Okay, so it's kind of like a summary. That's why I'm going to spend a little extra time. It's kind of like a summary objection that tries to bring back to life the other points, right? And so I'm going to close it cleanly and decisively. It's important for you, the reader, or those of you watching this video. All right, here's his objection. The authors conclude that equation 33. Let's go back to 30. Oh, we're on still. All of it, right on these things. Because, yeah, everything is done after you pass this point, but it's pretty much already done anyway. All right, the authors conclude that equation 33 must equal z sub s of n equal minus 1 to the power of n times n to the power of minus s. For all n is only true for real part of s equals 1/2. This is a hand wave. This is kind of stuff where I got to push back a little bit. This is a hand wave and not backed by a lemma about uniqueness of such representations. R going to 1 is not proven, and even if it were, it does not imply equation 33 equals z term-wise for finite n. So what this objection is claiming here is this. One, we're asserting, I and the co-authors are asserting term-wise equality for finite n. We're also asserting that what's claiming is we need a uniqueness theorem to justify comparing 33 with z. And lastly, we are relying on an unproven claim that r goes to 1. All three are based on misreading what the paper actually says. So break it down. Point 1, we do not assert term-wise equality for finite n. This is the biggest misread. We never claim equation 3 equals z for each finite n. What we do is define z to equal minus 1 to the power of n times n to the power minus s. And then what we also do is we derive equation 33 as a necessary condition imposed by the ratio identity. Then we ask whether that condition can remain compatible with the known form of z as n goes to infinity. This is an asymptotic consistency check. It's not a term-wise identity. So demanding term-wise equality for finite n is a category error. See? Category error. Point 2. No uniqueness theorem is needed. All right? It's not. Uniqueness theorems are required when you claim that like this representation uniquely determines a function. We don't claim that. Instead, our logic is if the defining ratio has a finite limit, then the resulting asymptotic form must be compatible with the known asymptotics of z sub s of n, right? That is a necessary condition argument, not a uniqueness argument. Necessary condition arguments do not require uniqueness lemmas. Lastly, point 3, we do not need to prove that r goes to 1. All right? This is subtle but important. We are not claiming the limit r equal 1 for all s. We're doing the opposite. I mentioned this before. We're doing the opposite. All right, let me break it down. Assume s is a 0 of zeta. Next, assume the limit r equals the limit, just the letter r. We're going to make that be the limit of r sub s of n. Let's assume that limit exists. And then show the compatible values. They're either r equals 1 or r equals 1/2. That's what we're doing. There's 2 more steps we're doing, but that's completely legitimate right there. We're just showing, hey, these are the compatible values for that. 1 or 1/2. Then we're going to show the case for r equals 1 forces real part of s equals 1/2. Hence, all the zeros. Actually, kind of forces it to be r equals 1 forces the limit r equals 1/2. So even if you try to plug in 1 r equals 1/2 comes out. If r equals 1/2, that implies real part of s equals 1/2. So if that's the case, those are all the zeros of the zeta function. Any zero must satisfy real part of s equals 1/2. That is it. I'm going to go over that again. Assume s is a 0 zeta. Assume the limit r is the limit of r sub s of n. We're assuming it exists. Then we're going to show the only compatible values are r equals 1 or r equals 1/2. 2 groups, one possible, or those only ways possible. And then we're showing even if we let r equal 1, it's still going to reduce to r equals 1/2. There is no way around r equals 1/2. If r equals 1/2, that directly implies reverse implies real part of s equals 1/2. So we narrow down to 2, say 1 is not possible. The only one that's possible is real part of s equals 1/2. That's it. So r sub s of n going to 1 is not a premise. We don't rely on it. It is one of the 2 logically possible outcomes under the hypothesis that the limit exists. I hope that makes sense. Here's why our conclusion is valid. The whole proof is. The critical logic structure is the hypothesis is this. S is a 0 of zeta with real part of s greater than 0. Okay? We have another hypothesis. The limit r equals limit r sub s of n, and that exists. And then analysis of that. Algebraic consistency yields only 2 possible limits. Elimination. Both possibilities force real part of s equals 1/2. At no point do we claim unconditional convergence, term-wise equality, or uniqueness of representations. So the objection is attacking claims that aren't made in our paper. The final objection says we require term-wise equality for equation 33 with z or uniqueness theorem, or that we assume r goes to 1. None of that is true. The argument is asymptotic and conditional, assuming the limit of r exists. We derive necessary algebraic constraints and check them against the known form of z. We never claim finite inequality or uniqueness of representations. The contradiction off the critical line arises from asymptotic incompatibility, not from a term-wise identity. Okay? Now, let's sum it all up. Objections 11 through 15 all stem from the same misunderstanding, treating our argument as a reconstruction problem instead of a necessary condition or asymptotic consistency argument. Once you understand that, then none of those objections survive. And I thank you for your time. And if anyone else has anything else that they find that, because this is really useful for finding typos, we did get a typo out of this, so that's awesome. And I can go fix that and make it a little cleaner, so for the other readers. But I thank you and have a good evening. I will see you in the next one.